Hello everyone, welcome to August Piowa. My name is Nick Stark. I am a senior reverse engineer at Hewlett-Packard Enterprise. I work in the networking business unit, taking apart networking appliances, looking for security vulnerabilities in network appliances and all the associated software that runs the infrastructure that powers those sort of cloud-enabled network appliances. So today, I'm going to be talking about a tool I built in Python to help me in the task of reverse engineering raw binary files. And so I'll kind of describe like the problem statement and then how the tool works, the evolution of how I built it, and we'll talk about like why someone would want to use this so that you can get an idea for like how I've applied it since I built it. So raw binary files, so if you have an exe file or some other compiled program on Windows or Linux or Mac OS, those programs as they exist in the file have metadata in the header of them. And for like Windows, that's portable executable 32. For Linux, that is ELF, and for Mac OS, that is Mach-O. And that metadata actually contains a lot of information that I as a reverse engineer need to know in order to reverse engineer the program. So if I don't have that metadata, when I try to load a program into my reverse engineering tool, whether it be Ghidra, IDA Pro, Binary Ninja, you're missing a lot of information, a lot of context that's very necessary in order to do a good job reverse engineering the program. And that includes things like mapping strings to memory locations and mapping functions to memory locations. All the data that you need to do that successfully is in that metadata header. And so there exist programs that do not have that metadata header, and that's things like boot ROMs, the very first code that runs when a processor initializes, bootloaders, things like U-boot, some implementations of grub2, things like that, where there's no metadata available to tell you where in memory that program is going to live. So that's what my tool does. My tool figures out where that memory location is, and if there is an offset into the file that the code begins, it determines that as well. A lot of times these raw files, these raw binary images have some sort of header, but it's a proprietary header that there's no documentation on. It's something that a vendor created for their own purposes, and the only place that it's recognized and understood is on the hardware itself. So in those cases, the actual instructions that execute are somewhere beyond the zero index of the bytes in the file. And that's the first thing my program does. The first thing it does is it attempts to disassemble every instruction until it gets to a valid sequence of instructions that's larger than 10,000. So you can get false positives, especially on Intel architectures where there's no alignment for instructions. Like on an ARM processor, ARM32, all the instructions are 32 bits long, for their 4-byte instruction set. So you know that every 4 bytes is an instruction. Well, Intel instruction sets can be variable bytes in length, so you have to disassemble every single byte, and the context of what it is depends on where you are in the file. So that's why I added that kind of like heuristic approach to discovering where the instructions begin. Let me get my slide deck up. By the way, I generated this slide deck with ChatGPT, so it's kind of minimal. And I'll show, as a bonus, I'll show you the prompt I use later so if you ever want to do that do this little trick where you don't have time to create a slide deck. You can just use ChatGPT. So yes, so the file offset where the code begins and where the code is going to exist in the memory of the hardware that it's being loaded on. Without that base load address and the file offset, if necessary, your disassembly or your decompiler results as provided by your reverse engineering framework or tool set are not going to be very accurate. They're going to have a lot of problems, and you are not going to be able to do a very good job as a reverse engineer of determining what is going on with the program. So the main areas you see these kind of raw binary files are component firmware. Like in Linux, that exists in the Linux-firmware repository, and that's like different proprietary blobs that get loaded onto webcams and Ethernet or WLAN network interface cards, things like that, like low-level component firmware for different things that exist inside the computer but are not the main processor or main memory. And then additionally, bootloaders. If you've ever heard of U-boot, it's commonly used as a second stage bootloader in embedded products. A lot of times, U-boot images do not have any sort of header. Yes, if you compile them yourself, you can get a version that has a header, and at that point, your reverse engineering tools will be able to look at that header and format the disassembly and decompiler results appropriately. But if you're using something that you're extracting from a live device, you're not compiling the bootloader yourself. You're extracting it from a firmware image or pulling it off of a SPI ROM chip or something like that. And in those cases, those are almost always raw binary images that do not have any metadata associated with them. And actually, when I was testing this tool, I tested it against a bunch of U-boot images. I compiled like 4 different U-boot images targeting different system on a chip boards. And then since I compiled them, I knew where they were going to be loaded into memory. And I used my tool with those files that I generated to make sure that it outputted the right memory address and the right file offset, because I knew those beforehand in this case. And in the 4 test cases I did, they all returned the right address. They just took the ARM images I generated took 2 weeks to process. And I'll talk a little bit more about the resource constraints of working with this tool I built, because it does require a fairly extensive amount of system resources to run. But that's just one thing I noticed. Like when I was running these, I ran them on an Intel processor, and the Intel U-boot images only took a few days. But the ARM U-boot images, which is a different processor architecture, that we're trying to analyze on an Intel processor architecture, like that took a lot longer. And the last test I did was a MIPS architecture, a big Indian MIPS architecture U-boot image, and that took a long time too. I mean, it took almost as long as the ARM image did. So yes, I guess back to my slide deck. This is something that's almost exclusively in the realm of reverse engineering. Like as a software engineer, this is probably not a tool you would need to use on a day-to-day basis. And as reverse engineers, there's basically 2 forms of reverse engineering. There's malware analysis and like security research. So, and by security research, I mean trying to discover security vulnerabilities in software you don't have the source code to. So that's the main audience for this. And I know this is a group of primarily software developers. So I'll talk a little bit about how the program works so that we talk more about the software development aspect of it and not just like completely focus on the security aspect to it. I went over this already. So the point I want to draw out from this is that this program, it's basically just a Python script, really. It has a few shell scripts that make it a little easier to run, but the main Python script uses what I would say are two different heuristics, one for the file offset and one for the base load address. I kind of talked about the file load offset already, about how we iterate over each byte and try to disassemble it until we get to a condition where the disassembly successfully recognizes 10,000 instructions. That's a heuristic approach, right? Like that's not going to be accurate 100% of the time. And I will be the first to admit that this tool is not going to be accurate for every single raw binary image you supply to it. I tested it against a few proprietary U-boot instances, and it was not able to find the file offset or the load address. So I know there are instances where these heuristics fail, but in the 24 times I've used this since I built it, I would say 18 times it's provided what I needed. So it's provided valid output in terms of the file offset and load address. So the heuristics aren't perfect, but they're not bad either. The second heuristic in terms of figuring out the base load address, this is a little more complicated, and I use a little bit different heuristic than the file offset. So when I'm trying to determine the memory load address for the raw binary image, I actually use a brute force approach where I take the file, I load it into a reverse engineering tool, in this case Ghidra, because it's open source. It's free to use, and it works really, really well given that it's free and open source. So it has a command line integration, and the Python script basically crafts a command that loads the raw binary image into Ghidra for every possible base address and file offset combination. So you'll know that by the time you're trying to create this large Ghidra project that contains all of the potential base addresses, you'll know the file offset already, or else you won't get any good results out of the rest of the process. So assuming you know the file offset, it creates basically a hash map between the file offset and the base address to test. And so at that point, there's a giant Ghidra project, takes up hundreds of gigabytes of disk space, and the script I wrote then calls basically analyze. And so then Ghidra goes through and analyzes each one of those instances of the raw binary, and it measures how many strings resolve properly. And the one that has the most strings that resolve properly is the base address offset. That's where the reverse engineering tool, in this case Ghidra, found the most cases where the strings line up with the rest of the source code memory address accesses, or I mean not source code, the binary memory access addresses, and then the script outputs that data, and you can see it in the terminal. There's a few convenience functions written into the script to write it to a file. You run a task or a process that runs for 2 weeks in a terminal. You probably don't want it to not write to the file system, right? In case your server reboots and then your work for the last 2 weeks, your results, they're gone. So I believe it does it by default, but you can fine tune where it writes it to. So definitely, if you are trying to do this on your own, if you want to play with this at all, make sure you have several, what's up?
Oh, and so what's the delta between like when you find the one with the most strings resolved and like the next closest?
The delta, it's usually pretty significant. Yeah, it depends on how many strings that are actually in the compiled program, but the difference is stark. I mean, it's you can tell the signal is pretty clear from all the noise. Unless we're talking about hundreds of strings basically in a given program. If you get less than 100 strings, the results kind of like are a little less reliable. I ran it on some of the MIPS firmware images in the Linux firmware repository. And after the fact, I learned that there was only like 37 strings in it, and that's just simply not enough to generate a reasonable result. And in fact, when I took the results from that run and loaded them into Ghidra to make sure that it would all work properly, I got garbage back, and it was obviously not very unsuccessful in that context. And if we want to talk about improving the tool, something like a check before you spend 2 weeks running it to make sure there are enough strings, that would be a good improvement. That would not be too hard to create. So maybe I'll add that at some point, especially if more people start using it. Really, there's the only people that have used this are a friend of mine and me. So I haven't worried too much about usability yet. I did work on several iterations of this tool, and I tried several different heuristics. I tried one approach where I just looked at the most significant 16 bits, and whichever one of those 16 bits that had the most strings resolved to it was the no. So I measured the first 16 bits, and analyzing all of the 4-byte chunks of instructions, whichever of the 4 most significant bits, 16 most significant bits appeared the most in the rest of the body of the instructions, I would like output the top 10, and that was the heuristic, and that was very, very inaccurate. I mean, it worked in like one use case, and it didn't work in any others. I tried performing the Ghidra analysis on each individual like base offset individually, but at that point you have to spin up the entire JVM and Ghidra process every single time you want to analyze, instead of just importing it all into one Ghidra project and then running the analysis over the entire Ghidra project. That saved a significant amount of time. That was a really useful optimization, because I wasn't scaffolding up the JVM and tearing it down every single time I wanted to analyze a potential base memory address. So that's kind of the trade-off. That's kind of the path, the progression I took. It was about 3 or 4 iterations, and I'm actually pretty happy with where it's at right now. So I think this definitely is the most accurate. Not perfect, but it's in its current form, it's definitely the most accurate iteration that I've done of this tool. It does use a ton of disk space. And that kind of depends on how big the raw binary program is. Usually these programs aren't more than half a megabyte. They're pretty small because they really don't do much. They're just it's usually some sort of bootloader that's responsible for finding where the Linux kernel lives on a storage medium and then loading the Linux kernel into memory and then transferring control of execution to it. So they're not large programs, they're not multi-megabyte in size programs, generally speaking. But the larger the input program is, the more disk space. And at 500K, it's easily 300 or 400 gigabytes of disk space. So when I was running this, I was running it on like a giant Windows server with like 2 terabytes of NVMe RAM. Like the disk I/O will become a bottleneck in this process if you run it against something that has slow disk writes and reads. So I definitely recommend, if you want to play with this in like a non-hobbyist kind of fashion, do it on something with a fast disk. Yeah, so that's okay. So I'm gonna kind of like go over to the repository and kind of just walk through some of the files. So there's a Python script that utilizes Ghidra by shelling out to it, essentially. There are a few Ghidra scripts that are necessary for processing it. Basically, what these scripts do are count the strings that are referenced successfully, and what does this one do? Sets the program attributes. Oh yeah, this one, actually the only one that's reused is this, the count reference strings. It takes the base address from the folder structure in the Ghidra project, which is how I stored the potential base address to process with, and it maps the total number of reference strings to that base address. So it's not super complicated, but they are necessary for the run. And I tried to create like some helper scripts, like the Python script. I'll open it up here. It has a lot of arguments in an effort to try to make it as flexible as possible, so that if anyone wanted to come in and only analyze a certain subset of the 32-bit address range, they could. And that's why you see the start, the end, the interval, the offset. All that stuff is to allow someone to fine-tune this so that it might take less time.
So like, this is entirely in English, like it's not necessarily accurate Chinese?
No, it's all in English. Yeah, I wrote it all, and I don't know anything other than English and Latin, so yeah.
So like, if you like
It wouldn't, so it wouldn't be able to process it because it wouldn't be, the question was, if I inputted a Russian or Chinese language file, would this be able to recognize the input? And the answer is no, because it wouldn't be able to find any CPU instructions in that file. And well, I mean, I guess with Unicode data, potentially it could give you false positives, but it's not going to find 10,000 instructions in a row. And so it would just, I'm pretty sure it would just say file offset not detected and exit out. So that's part of the process, is if there's no file offset determined in the input file for the code, the instructions, it'll exit out before it does the rest of it.
If you like just fed in like a global lexicon, common, right, would that like blow the runtime completely out of water?
No, it's the same thing. So like instructions use a larger character set than like Unicode and ASCII. So you're dealing with the entire range of 0 to 255. And if you threw like something that's a lexicon, like a dictionary or something into it, that's going to be, well, in English, that's going to be probably entirely in ASCII. In a foreign language, that's going to be in Unicode, right? So those are not going to be recognized as sequential CPU instructions. And at that point, the program's going to exit out and say, like, I don't know what to do with this. It doesn't look like it's a executable code. Does that make sense?
Yeah.
Does that answer your question?
Yeah.
Okay. So this has all the arguments. A couple other things I'll mention here. This language ID is very important. Language ID is a Ghidra-specific term for the instruction set architecture, like Intel or ARM or MIPS, and it's a very specific format that contains the bitness, the Indian size, the big Indian or little Indian, the number of bits per CPU instruction, like if it's a 64-bit processor or a 32-bit processor. Just to note, this will not work on 16-bit processor, like a microcontroller, like a 16-bit because if you think about it, a 16-bit microcontroller program is going to anything will disassemble into 16 bits because it's only 2 bytes, right? Like, so if I try to disassemble just random bytes from dev u random, a disassembler program like Ghidra will be able to disassemble that. It'll be meaningless. The disassembly will not form a coherent program, but because it's 2 bytes, it can always disassemble it. So and honestly, like the 64-bit address space is way too large to work with in any like reasonable capacity. So this script, this program I have written really only works with 32-bit architectures. So, you know, that doesn't make a lot of sense when we're talking about like a laptop or a server, but it makes more sense in embedded scenarios where like almost everything still runs 32-bit. So yeah, that's what my bread and butter is like 32-bit firmware. So like this is really specific to kind of the work I do on a day-to-day basis, and it has little relevance to the modern world of large servers and you know, even like Graviton, something like AWS Graviton. Those are all 64-bit ARM machines. This would not be able to work with anything from that instruction set architecture either. Yeah, but so the point I want to make, there's lots of arguments, there's some sane defaults, but things like the language ID have to be passed in. And that's where these convenience scripts I wrote are kind of helpful. Like, so I'll just open up the bash one. So, this does a couple of different things, but this doesn't look right. Let's see something. Yeah, this is where it is. So this will go through and install all of the dependencies and the tools that are necessary. And my goal with these scripts, like this install.sh is called from the run.sh. So the idea was to just provide an interface where a user could go run.sh file name, and then it would take care of everything else for you, including determining the instruction set architecture of the program file you're feeding it. And that's a really complicated process, but thankfully, there is a tool already built that does that. It's called CPURec. I added it as a Git submodule to this repository, and these scripts, these convenience scripts I wrote, will use CPURec to determine what instruction set architecture the file you gave it is. And if it can't determine it, or it can't determine what it is for the entire file, it will exit out and say, I don't know what this is, I don't know what to do with it, so I'm exiting now. So that was kind of like the usability aspect I brought to it. When I was testing it, I did test this using the convenience scripts I wrote, and with the U-boot, I ran 4 U-boot tests, and they all returned the proper result. But like I said, there are definitely things, programs out there that would not fare well in this tool. And honestly, at this point, without adjusting some of the heuristic numbers, like instead of using 10,000 sequential instructions, using 6, other than adjusting those kind of parameters, I don't know how to improve this anymore. So it's kind of at the point where I don't know how to structurally make the software better to return better results, and so I'm kind of it's setting it aside and not working on it a bunch anymore. It works for my use cases. I use it at work fairly often, and it works for what I need it for. But I will be the first to admit it's not perfect code. So. Let's see if there's anything more in my slide deck. Oh yeah, I promised I would show you the prompt I used to generate it. So let's slideshow this. I had a very compressed time schedule to develop the slides. So I did use ChatGPT, and this is the prompt I used. It includes the description from piowa.org, the meetup description of the event. And I just gave it the URL to my Git repository, and it pulled it in and generated about 10 slides. In fact, this is the only slide I added to the entire deck. So I just thought that was kind of a cool tip. This is in case you have a project you want to present on at Piowa, but you don't want to spend a huge amount of time developing a slide deck. You can use this technique to present at one of the next meetings. So this is the address. You can look me up on Blue Sky if you want to connect. At this point, I'll just open it up to questions if anyone has any questions, or if anything didn't make sense. I recognize that this is kind of outside the domain of a lot of software engineers. So if I use terms that didn't resonate with you or make a lot of sense, please don't feel afraid to ask, because I do this all day long, and sometimes I forget that most people don't. So any questions? Any comments? Yes?
Is the number of ERs at the end your version of semantic versioning?
That's great. The question was, is the my way of versioning the code, and no, it's always been called that. There was some movie I saw, or maybe it was a South Park episode, where they were talking about something that ended in ER, and it was every time they said it, they said "Arr," and so that got caught in my head when I was creating the repository, and that's why I did that. I should probably rename it. Probably people look at that and they're like, this is just a joke, so they probably don't proceed any further. But thank you for that. That was a good comment.
Or perhaps if you read it from the end of it in reverse.
Oh, like Little Indian style.
E.
Oh yeah, there you go. Yeah. I'm not that sophisticated though. I don't make jokes that funny.
Can you bounce stuff through an emulator and look for words like error or hard zero or stuff to figure out oh, this must be what it's called against because it generated a sensible result even though it's an error result? Is that a thing you can do?
Yes, but that is all handled by Ghidra, and so that's that. The logic in all of the code that does that is contained within the reverse engineering framework, which is called Ghidra. Ghidra is a very, very sophisticated tool. It's built entirely in Java by the National Security Agency, and they've invested a lot of time and energy and resources into providing this tool. And when you download it, it's a compressed zip archive that's 450 megabytes in size. I mean, it's a very, very extensive tool set, and it's the ability to do that, to analyze like structured binary data to find out where the error conditions exist and how they relate to the rest of the code is purely in the domain of their tools and not something that I can claim any credit for. All right, well, thank you very much. I really had a good time presenting, and yeah, thank you.